Hey everybody, it's Tony from Adafruit, and I'm doing a little bit of a stream on the Raspberry Pi, so a little more off the cuff and kind of less scripted as some of the previous streams, so don't have the fancy intro, just trying out some new things. And basically, so I wanted to celebrate the first anniversary or the fourth anniversary, however you want to look at it, for the Raspberry Pi. So 4 years ago it was released, and a really neat feature in the last Rasbian operating system release is better OpenGL support, which is like the graphics library you can use for 3D rendering. And so I thought I'd do a little bit of some experiments with playing around with OpenGL. We'll kind of turn on the new OpenGL driver and just see what it does and how it works, and maybe play a little bit with some Python OpenGL programming. So it's been a long time since I've done graphics and OpenGL programming, so we'll kind of learn as we go here, pick up some old tricks and things and see what happens. So let's jump to this view right here. So this is basically I've got a web browser, and then in the upper right corner this is the HDMI output of my Raspberry Pi. This is the Pi 2. I don't have the Pi 3 yet, so as soon as I get that, I'm sure we'll do some streams and stuff with that one. But I've got the Raspberry Pi output, and then that's me in the corner down there. So what I wanted to do was maybe real quick just mention what's new. So last month there was a new Rasbian release which brought some pretty interesting changes. So there's a post on the Raspberry Pi blog that goes through what's new. But the big thing it talks about is this experimental OpenGL driver. And so one thing with the Raspberry Pi is that the 3D graphics support has been a little limited because the driver support hasn't been like fully opened. And in the past year or so, I think they opened up more of the documentation around the graphics driver on the Raspberry Pi. And so now there's actually been some interesting open source implementations. And so somebody named Eric Anholt, he's been working on getting a more open GPU driver for the Raspberry Pi. And they've got it in the latest kernel from what I understand. And I don't know if this is the final version. I think they're probably still tweaking it. But the gist of it is that it gives you better OpenGL support. And so OpenGL is the graphics library that you can use for kind of hardware rendering, things like video games, but even stuff like your normal desktop can use that, like for 2D graphics. And so previously with the Raspberry Pi, or maybe before this driver, from what I understand, I'm not a super expert on this, the Raspberry Pi supported a smaller version of OpenGL called OpenGL ES, which is like more for mobile platforms. And it's like a subset from what I understand, so it only supports maybe more limited capabilities. And the problem is most of your desktop software, like games, are written for the full OpenGL version, which the Raspberry Pi didn't support. But this new driver apparently gives you that full OpenGL support, so you can go in and take something you wrote for a computer, like a game, for a desktop computer, and compile that and run that on the Raspberry Pi. And in theory, over time, it'll probably add more features and maybe get more performance. So the blog post here just kind of talks about it. The big thing is there's a new config option in Raspi config to turn on this new driver. And so we'll go through that and kind of see what happens. So first, I just wanted to go to my Pi and install like a little OpenGL demo, and we'll run it right now on the Pi when I don't have the new graphics driver enabled, and then we'll come back, enable the driver, run it, and see what happens if it changes. I actually haven't done this yet, so we'll see if it actually makes a difference. So I'm going to connect to the Pi. I'm just SSH'd into the Pi right now, and what I'm going to do is install a library called Pi OpenGL. And so this is a nice little wrapper around OpenGL. It basically gives you all of the functions, because OpenGL is actually like a C API, a C library. So to use it from Python, you need some kind of a wrapper around it, and Pi OpenGL looks like a great one. So let's see, let's install Pi OpenGL. Now from their website, they kind of tell you a little bit about it. They say you can do a pip install. I did this in advance, and I realized there's a few extra things that you need for this. So you need to install the Python development tools. So sudo apt-get install python-dev, and then might as well also do python-pip just to make sure we have the Python pip tool. I installed these both at a time, so it's just going to tell me I already have them, but that's what you want to run to install them. Now to install this library, it just says to do a pip install for Pi OpenGL and this OpenGL Accelerate. So let's do that. oops, let's go back to, okay, so pip install pyOpenGL, pyOpenGL accelerate, so we'll hit this. And then there's one extra thing to install that you might run into. So by default, it doesn't install this library called GLUT, which is like a OpenGL utility library. And it gives you kind of the glue because OpenGL is like an open standard. It's a standard for graphics APIs. This is telling me something failed here. So couldn't create, I need to run it as sudo. So I ran pip. If you ever see a failure like that, basically it can't write, permission denied, it means you probably need to run as root. So rerun that as root. But anyways, OpenGL is just a generic, it's like a definition of what a graphics API should look like. So you can write a game and you can write against the OpenGL APIs. And then in theory, you can go and run that on any hardware that supports OpenGL. But the problem is every platform has some platform-specific GUI, like how do you create a window? That's different between Mac OS X and Windows. There's vastly different APIs to do that. And so GLUT kind of is this little intermediate layer that gives you some cross-platform window APIs, just enough stuff to create an OpenGL window and kind of get started. And then it also has some extra stuff too that hopefully I'll be able to play with, of like some easier rendering primitives and things. Stuff that's a little bit outdated, and I'll talk about that in a second. But it's still a handy library. And if you're learning OpenGL, especially in schools and classrooms, you're probably going to use the GLUT library because it's pretty simple and easy to kind of get you going. Because that's one big thing, is that OpenGL, it gives you a lot of good rendering stuff, but that's it. And when you want to build something interactive, you probably want like keyboard input, mouse input, and you don't get any of that with OpenGL. So you've got to find like another library. There's other good stuff. So like if you're making a game, the SDL library, the Simple Direct Media Layer, that's a really popular one. Really popular with two-dimensional games, but you can use it with OpenGL also. And that gives you a real nice like high performance counters, so you can tell like how much time has elapsed at like a nanosecond level. That gives you like keyboard and mouse input. That's real nice and easy to use. So pyOpenGL is installing. It's compiling a little native Python extension, because it's basically just a direct wrapper around the OpenGL C APIs, which is nice in that you can pretty much directly take OpenGL code and run it with very few modifications in Python. And I like doing it in Python because there's a little bit of performance overhead, but it's so much simpler as far as like creating a buffer of vertices and rendering them. The syntax is much easier, like, and this pyOpenGL library just takes care of a lot of the kind of grunt work for you here. So this shouldn't take too much longer. And maybe while we wait here for a second, I'll just kind of show you the web page. So this talks a little bit about pyOpenGL. It mentions a whole bunch of things it supports, and it's actually pretty full-featured from what I saw. So OpenGL 1.1 to 4.4, and I'm pretty sure 4.4 is like the most cutting-edge version of it. So maybe I'll talk a little bit more about kind of the history of OpenGL in a second, but OpenGL has seen some pretty major revisions, especially after version 2.0. So there's kind of like old OpenGL, which has this mode where you create objects, and it's not super efficient as far as how graphics processors work these days, but it's a little easier to work with because you can do things like say, hey, I want to create a cube, and so here are the 4 points, or maybe the 8 points that make up this cube, and it's easy to do that in older OpenGL. Whereas after OpenGL 2.0, they went to this programmable pipeline that I'll talk about, and that it gives you a lot more flexibility. Like you can define exactly how things are rendered, but they lost a little bit in that transition. It's not as easy to use newer OpenGL versus older OpenGL, and you'll see some of that a little bit later here. So okay, cool. So pyOpenGL installed, and then the other little you need to do sudo apt-get install freeglut3. I think if I remember correctly, freeglut3, and let's put freeglut3-dev. And so this is that GLUT library I was talking about, the OpenGL utility library. And this is actually a fork of it, or not really a fork, I think it's like a re-implementation, because the original GLUT is, from what I understand, not really maintained anymore. I think the OpenGL, the Kronos group that kind of owns OpenGL, owns GLUT, but it hasn't seen updates in years. So FreeGlut is kind of like a more modern, backwards compatible, like it's compatible with GLUT, but just an open implementation that's a little more maintained for it. So I'm installing that, and then in a second it should be done. And once I have that, then I'll jump up to the Raspberry Pi in the corner here that's just kind of been doing nothing, and we'll install a little example and see if we can get going with that. The only annoying thing about this Pi OpenGL library, though, is that when you pip install it, you don't get any of the demos or the example code. So I'm just going to go and just manually copy the zip file here, and we'll go and install that once this is done installing the GLUT library. So that once I get the examples, then we'll be able to run some of these and see kind of what the performance looks like, and then maybe we'll take one and kind of modify it a little bit and see if we can build something interesting from it. And then maybe kind of while I wait for this too, I'll go into something I want to talk about also. So like I was saying before, there's this difference between modern and maybe classic or older OpenGL. And I won't get super into it, but basically there's a really good website, and I'll put this in the description when the video goes up, this modern OpenGL tutorial for Python. Really, really interesting and great little blog post or tutorial, well worth a read. So this talks about the modern version of OpenGL, and actually this intro here is really good. So it talks about kind of the history of OpenGL. It's from the early 90s. Up until now, and you can see this big split between the fixed pipeline and the programmable pipeline right around like 2003, 2004, which is right when I was in school and learning OpenGL, so it was a little bit fun kind of dealing with that. But basically the fixed pipeline in OpenGL means that there's only one way to render things, and it's baked into the hardware. And when I say rendering, this is actually kind of an interesting thing. So when you get down to the physics of what you're looking at in the real world, like anything, like what your eyes see, it's this equation, the rendering equation. So like everything in a computer graphics movie, like a Pixar film, all of that is just trying to recreate this equation. And I remember learning about this in school, and I thought it was really cool how simple, quote unquote, this equation is. It's really just an integral. Like you're taking a 3D integral, so you've got a point in space x, and everything visible from that point x is just all of the integral of all the incoming light, and then the integral of any light that this thing emits. And there's this thing called the what is it, the BRDF, the bidirectional reflectance distribution function, which kind of tells you what is the material of this object and how does it reflect light. And when you get down to it, all of computer graphics and all of rendering is just trying to solve this equation. And you can't like analytically solve this, or for a complex scene, like this room and me and the lights hitting me, it's impossible because there's just too many variables. It's too big of a space to solve this perfectly. So everything is just trying to estimate this equation, and trying to do, like, sometimes there are hacks that make it a little simpler. Sometimes you take like a Monte Carlo method where you just randomly kind of throw darts at a wall and pick different points and hope that you get a good distribution of things. But I just think it's kind of fascinating. It's one of these like little, it's a very compact looking equation that expands into this massive thing. It's everything you see is just defined by this equation. But that's what the fixed pipeline was doing, is that it had its own implementation of how to render things. And, it's kind of fixed to a certain style of rendering and shading, like Phong shading, where, you can do smooth shading with specular highlights, which is kind of the shininess and things that you see. But you couldn't change that. So like, if you had like maybe a shirt that's not shiny and, maybe it glows in a certain way or something like that, if you couldn't figure out a way to model it in OpenGL's fixed pipeline, you just couldn't render it. The programmable pipeline came about 10 years ago or so, just as a way to kind of go beyond that fixed pipeline. And so the programmable pipeline, you actually put in code that says, okay, for this point, like on me, maybe if I'm rendering a model, how should this point be rendered? Like, what is the exact lighting equation to use? And it can do all kinds of fancy things, like you can store, maybe the material in a texture and look that up and use that to compute things. So you have a lot more control in the programmable pipeline. But the problem is, it's a lot harder to use that programmable pipeline, at least to get started, because just to render a cube, you have to put in, a shader that says, here's how to deal with just the ambient light in the room, and here's a diffuse light that maybe just has a soft shading, and here's a specular light that gives you some shininess, and it gets very complex very quickly, especially to begin with. When you're just starting, you just want to say, hey, I want to render a cube and a sphere, and just do it. Like, here's the position I want to put it, here's the color I want these things to be. And old OpenGL with the fixed pipeline was very easy to do this because it actually has all these functions, things for creating a vertex, which is like a point on an object, things for setting the color, creating lights, versus in the new OpenGL, the modern world with the programmable pipeline, you have to do all that yourself, and so it's a little more difficult. But anyways, long story short, this page is great. It tells you how to do the new modern way of using OpenGL. It's modern OpenGL is a lot faster. It has a lot more emphasis put on using your graphics hardware efficiently. So because your graphics hardware is just another processor that's more optimized for dealing with pixels and vertexes and 3D objects, and so all of OpenGL is really just how to tell that graphics processor to render things. And old OpenGL with the fixed pipeline doesn't work well with processors, with the GPUs that we have today. So modern OpenGL has a lot less of a high-level abstraction. You're dealing with, like, here's a chunk of memory on the graphics card, and I want this to represent maybe points in a 3D model, versus in the old OpenGL world, you just say, here's my 3D model, go render it for that. So anyways, let's see how this is doing. Okay, so we just installed that GLUT tool. Now I'm going to go to the Raspberry Pi, just up in the corner here. And actually, first I want to install those examples, like I said. So I want to wget the package here, this little zip file. So this is the Pi OpenGL demo package, and it should have a zip file here. Yeah, so just unzip this. And this is just giving me a bunch of examples. And now if I jump over to my Raspberry Pi, I'm going to grab a different keyboard here, and I'm going to open a terminal on this, and hopefully, let's see if I can make this a little bit bigger. Might be able to read this a little more easily. I'm just going to go in and run an example. Alright, so make this terminal a little bigger. Let's see if I can zoom in on this. Let's see, maybe preferences have font size, yeah, display, nope, style, is that in here? Yeah, here we go, monospace 10, let's make this bigger. Let's go, 40 is probably a little too big, let's do like 20. Okay, yeah, that'll probably work. Okay, so font, there we go, well, whatever, it's full screen. Now let's see, let me go in here and let's go to the examples. So it's in this Pi OpenGL demo folder. And I want to run one of the examples in, so it has a example folder here, oops, just ls into here. So they have GLUT examples, and GLUT was that toolkit library I was talking about. There's one in here called GL Gears, I think. Yeah, let's do Python gears.py. And this is kind of a classic OpenGL example where it's some rotating gears. And so you can kind of see it's in the upper right hand corner here, and it's kind of funky, like something is not right with this. So I'll see if I can resize this. Well, first of all, you can see it's super slow, and actually behind here it's telling me the frames per second, so it's running at like 5 frames per second. So that is not going to cut it for any kind of a graphics application. You can see it's got all these weird artifacts, so something's not right with the rendering. And ultimately what's happening is there's a software render, so all of this rendering is just being done by the Pi CPU, which means it's really slow, and it's not basically able to render as fast as like the GPU. It's not being done by the GPU. So let's go in and let's flip on this special OpenGL graphics mode and see what changes when we run this again, how this is affected by it. So let's see, I'll close out of this, and we'll come back to this. So to turn on the new OpenGL mode, you want to use the raspi config tool, and you need to use the command line version of it. So I'm in an SSH terminal on the left here, so I'm just going to run sudo raspi-config, and you have to be using the latest version of the Jessie operating system. Like I think it's the February 2nd image. I'm using the February 22nd or 26th image, so grab a recent image and it'll be in here. And it's down in the advanced options, and there's a GL driver option. So it says enable experimental GL driver for the desktop. Yes, let's enable that. So it's enabled, and now I'm going to finish, and now I need to reboot. So we'll see the Pi reboot, and hopefully it comes back on the screen up here. So this is just going to flip some things. I don't think it's a device tree thing that's changing. I think there's probably something at a lower level that it's enabling. But this is going to load up in a second here. And the interesting thing is that this driver actually, from what I understand, uses 3D acceleration for the normal desktop. So like your Windows and 2D browsing will be 3D accelerated. So in theory, this will be a pretty nice speed up just for the normal Rasbian desktop. And I'm very curious to see how this will work on the Pi 3, because if you've got a faster processor, you might be able to use this as like an everyday computer and not be super slow. So okay, so the Pi is back up, and let's go back, and I'm going to go and run that example again. So let's go into that Pi OpenGL demo, and let's see, where was that thing at again? Yeah, Pi OpenGL demo, GLUT demos, and then yeah, the gears. So Python gears .py, and let's see what happens. Okay, now this is interesting. So first of all, let's see. Let me see if I can make this a little larger. So wow, okay, big difference from what we saw before. The colors look great. So this is how it should look. You're not seeing that weird flashing. And look at how much faster it's going. Like this is perfectly smooth. And if I jump back here, you can actually see it's telling me it's running at about 60 frames per second. So, and that's probably locked into like the refresh rate. There's maybe like a VSync or something that's enabled with this. But that's quite a difference. I mean, that's pretty impressive that how fast this can run and how nice it can look. Oh, and I can see, you might see it looks like it's not spinning. It's actually spinning so fast on the computer monitor I'm looking at here. When I'm looking at the output from the capture card here, it looks like it's going in reverse, and that's just because it's running so fast. You're getting a weird sampling artifact. But that's pretty cool. So we've turned on the OpenGL mode, the experimental OpenGL driver. Now it's using the video card or the GPU on the Raspberry Pi, and it's using that to render all the triangles, because these gears are actually just 3D models. So there's a few hundred triangles that make up this scene, and the Pi GPU is really optimized for drawing these triangles. So that's kind of cool. Okay, I'll close that, and let's see, let me kind of just move this window out of the way a little bit. So what I wanted to do next was maybe just play a little bit with OpenGL and the Python code for these demos, and we can kind of just see. I wanted to see if I can make a birthday cake 3D model for the Raspberry Pi. It's not going to be fancy. It's just going to be some cylinders, but we'll kind of go from there and see what we can do. So what I'm going to do, let's see. Let me make sure I'm connected to my Raspberry Pi from my Mac. So this is a really neat tool, by the way. It's called Mac Fusion. If you install this and you install SSHFS, I want to say, you can basically set up your Mac so that it can mount your Raspberry Pi, and it'll look like a drive, but it's actually just talking to the file system on your Raspberry Pi, like using SSH. So I'm going to click this mount, and it's going to mount my Raspberry Pi. Now I can open up my text editor, and this should be connected to the Raspberry Pi. So like, let's see, I should be able to see that Pi OpenGL. Yeah, so here's the Pi OpenGL folder with the demos. Here's the GLUT folder, and then let's look at like that gears.py. So this is the code that was running that gears demo. And so this is basically just using that Pi OpenGL library like I was talking about before over here. And it's implemented, that the gear demo, and it's kind of neat. You can go in and see how this works. way down at the bottom is kind of where the initialization happens. So it calls some functions to initialize the GLUT library, tells it, it wants to create a window that's 300 by 300 pixels, and then it passes a few functions. So there's like a draw function, a reshape function, keyboard function. These are just functions that'll be called when some event happens. So like the draw function is called every frame that needs to redraw the screen. The reshape function gets called if the screen resizes. And then the keyboard function, like when a keyboard key is pressed. That's where you can put in some input logic for this. So I wanted to start with maybe something a little bit simpler. Let's see, I'm trying to remember which demo I'd started with before, because there's some simpler ones. Yeah, I think the cube demo here is, yeah, this is the one that I want. So this is under the Red Book folder in the Pi OpenGL demos, and there's a cube.py. Now the Red Book, real quick, just to let folks know, this is a super interesting thing. It's the OpenGL Red Book. This is a classic book, and if you ever do OpenGL programming, you're probably going to be familiar with it. Whoops, let me go back here. So it's called the Red Book because it's red, obviously. It's the OpenGL programming guide. And there's a lot of versions of this, and basically, like for every major OpenGL version, there's a new version of this book out. Looks like version 3.0 is kind of the newer version, and so this gives you kind of like the, I wouldn't say beginner because it does assume you know how to code C, but it gives you kind of an intro to OpenGL and how to use it, how to get started. It's not like an API reference. This is more of like, here's how to draw a cube and spin it around, for example. And you can actually find versions of this online, like actually this glprogramming.com. But be careful, if you find a version of this online, look at what version of OpenGL it's written for. So this one's written for OpenGL 1.1. Anything with OpenGL 2.0 or less than 2.0 is going to be for that older fixed pipeline. And so that's not really the modern OpenGL like I was talking about before. It's still perfectly fine. You can use it. It's, everything's good. It's just, it's not really how, like a game today would be written in OpenGL. It's not going to be as efficient. But I think it's easier to learn and to get started with because it has functions that are a little easier to deal with. You aren't dealing with the low-level graphics card details as much. So yeah, the Red Book, definitely worth checking out if you really want to play with OpenGL. So anyways, let's come back. So this is one of the examples from the Red Book. It's basically just a cube, and here actually let's just run this example on the Pi and just see what happens. So I'll go up to the Pi again, and let's go to a different directory. Let's go to the Red Book directory, and let's just run the cube.py, and we should see, so you can see it just shows a little wireframe cube up in the corner here. So nothing too crazy, pretty simple. You press escape and it goes away. So now let's take this and I'm going to copy it and we'll just start modifying it. I'll make a new file in this directory. Let's call this Tony demo. How about cake.py, because I want to build a birthday cake for the Raspberry Pi. Alright, so I'm going to pull a few things out of here. This is kind of an old script. It says it was written in 2000, converted over, so there's maybe some style conventions and things that have changed a little bit. Let's see. It's kind of interesting. They took the C comment and made it a string. I mean, I guess that's the doc string for Python. That works. We'll keep it in there. What the heck? It can't hurt. This thing, I'm not sure what this build to system thing is, so I'm ripping it out. You don't really need that. This is just kind of the first line that says this is a Python script. So okay, now they actually try to be safe and import OpenGL libraries, and if it fails to import them, throw a nice error. I know these libraries exist, so I'm just pulling out this code. It's just boilerplate. And let's just fix some of the indent here. The other annoying thing is this file, the indentation is a little wacky. It's all 3 spaces when it really should be 4. So I'm going to see if I can fix that. I think Sublime Text has like a white space. Let's do spaces to tabs, and then maybe let's go back tabs to spaces. No, that doesn't fix it. Maybe it has like a re-indent function in here. Lines, text. No, I don't really see it. Alright, well, we'll deal with it. We'll just kind of go, we'll fix it as we go with this. So, okay, so this is actually not too crazy. This is the entire script right here. It fits on one screen, which is kind of nice. And I'll just kind of walk through. So the bottom is really where it starts running. The top are just some functions that are defined. Basically, you have to initialize the GLUT library. You have to tell it what display mode you want. And so you can pass in different things. This is just saying use single buffering. There's various buffering. There's like single and double buffering that you can do for kind of better graphic fidelity. Like double buffering, you get a smoother image. I'm not going to deal too much with that. It's more if you're making like a game. You can set the window size and the position. I don't know why this code, they put spaces in between the parameters. So let's go back to just kind of normal style. You create a window, you give it a name, and then they call their initialize function up here. So this code gets called. And this is just going in and calling, so these are OpenGL functions. So there's like a GL clear color function. And one really nice thing, the PyOpenGL library does have good documentation. So in their reference, and they actually have docs for all of the libraries they wrap. So like OpenGL, the GLUT library we're using, they even have some other libraries in here. So if I go into the GL reference, I can actually search for GL clear color. And you can see right here, so here's the clear color function. And it tells me it takes red, green, blue, alpha. So this is the color it should use when it clears the screen. And if I look at my code, it's just using 0, 0, 0, so just using black basically. The colors, if I remember, are floating point values that go from 0 to 1. So if I wanted to clear the screen in red, and what the heck, let's just change it and do that. Then I'd change like my red to 1.0, like full intensity. If I wanted like half red, I could do 0.5 instead of that. So we'll do that. The alpha color, that's just for alpha channels, which is kind of like transparency. And I always get it wrong. I always have to do it and see what happens. I think 0 is like not transparent at all, and 1 is fully transparent, but I might have that swapped. And it's pretty easy to figure that out, like when you assign an alpha value and then suddenly your thing is transparent when it shouldn't be. But that's just a parameter that lets you change the opacity of something. The shade model, so this tells OpenGL the fixed pipeline. So this example, and if it wasn't clear, this is using the old OpenGL fixed pipeline of rendering. And I'm going to keep using that in this example because I think it's easier to learn with and kind of get started with. But so I'm basically telling OpenGL, just do flat shading, which is like, I wouldn't say Tron style shading, but it's similar to that. It's like, each polygon is a single color and there's no shading on it. You might have multiple polygons that are each different colors, but they look flat and, very computer, like 80s computer graphic kind of style. And we'll change this to smooth in a little bit and kind of see how that changes stuff. But anyways, so that's the initialization function. Then it goes in and says, okay, I need to tell the GLUT library what my display and my reshape functions and my keyboard functions are. And so those are just the functions that are defined up above over here. And then it just calls this GLUT main loop function, which never actually returns. So this is just going to go and run, and it's going to call my display function when it needs to draw a new frame. It'll call my keyboard function when a keyboard key comes in. So that kind of processing happens. Now in my functions, let's see, we looked at the init function, and I'm just going to fix the spacing to be 4 spaces so that it's going to bug me forever as we go through. So the display function, it's going to go through and immediately clear the screen. So you can see it calls GL clear, and it's passing in this color buffer bit. Basically the GL clear function, in OpenGL there's more than just the color buffer, like the pixels you see on the screen. There's actually a depth buffer which tells you for each pixel what is the closest depth that was seen, and that's how you can actually like render, like if my hand is in front of my face here. If I was rendering, like, think of my face as an object behind here and the hand as another object in front of there, just doing that clipping to know, okay, like, this part of the hand is in front of my face, and if I'm drawing my face, don't draw the eyes because my hand is in front of it. That's actually pretty complex, and there are some relatively sophisticated algorithms that have come into play to figure out how to draw things without overlapping. The way OpenGL does it is it has a buffer for each point on the screen that says, okay, what's the closest object I've seen? And if I'm rendering a new object, like, let's say I have my hand and now I'm rendering my face, it looks to see, okay, if I render, the pixel for my eye that's covered up over here, is it in front of my hand or is it behind my hand? And if it's behind my hand, don't render it because it's occluded, it's not visible. And so that's a real fast and efficient way to do that. It takes more memory because each pixel now not only has to have the RGB color data, it needs some kind of a depth bit of data too. So it's a trade-off, but it works well for performance there. And that's one weird thing with OpenGL though, is that you have to manage those buffers independently. So right here, this isn't actually using the depth buffer in this example, but it's clearing the color buffer, so it's going to clear the whole screen of colors. This color function sets the current color for OpenGL, so it's setting it to white. Now load identity, the one big thing, and I'm not going to get too much into this, but when you get into computer graphics, you really realize that everything comes down to matrix operations. So everything is represented by kind of the three axes, the XYZ axis, and if you want to like rotate around the axis or move along an axis, it's really just linear algebra, like some matrix transforms that you can do. And rather than try and like have all these functions of like, okay, move along the x-axis, now rotate along the y-axis, OpenGL just says, here's some matrices, you can generate a matrix that defines that rotation and translation and just apply it to the scene. The load identity is just saying load up an identity matrix, which means a matrix with no movements, no transformations. It's like a default state basically. So every time it renders, it starts out and just clears any previous transforms that it had done, and says, okay, just start from a normal kind of space. Then the next thing it does is it creates the camera basically. So when it's rendering the scene, it does a transformation to say, okay, I want to make a camera, and this look at function is actually pretty powerful. So it's not a part of OpenGL, it's part of this GLU. It's not GLUT, but it's another OpenGL extension library. And it basically takes in a few different things. So it takes in the position of the camera, which is the top 3 points, the XYZ location. So this is creating a camera at 0, 0, and then 0.5 along the Z-axis. And the Z-axis comes out of the screen. I think that's right. I always get that one wrong too, and you'll learn very quickly whether it's right or wrong. But try to remember, positive Z-axis is coming out of the screen towards you, basically towards you if I'm kind of pointing at you. The second point is the point to look at. So this is basically saying, okay, slide back a little ways, pull out from the screen and look at point 0, the origin. So you're kind of looking towards the screen effectively. And then the third thing is the up vector, which says which way is facing up. And so that's like if I wanted to rotate the camera around, I could change the way this thing points. Right now it's just saying 0, 1, 0. So, oops, the Pi screen just died there. That's kind of interesting. Okay, there we go. Now it's back. So 0, 1, 0 is saying, okay, create a vector that's pointing up, straight up, because the middle axis, that's the y-axis. The y-axis goes up and down, x-axis goes left and right, and z-axis goes in and out. And so we have a vector pointing up that says, up is straight up, effectively. So, I'm not tilted in any way with this camera. And then the next thing is a scale function. So this is just going to change the size of whatever gets rendered after this point. Because like I was saying, OpenGL is all about matrices. And so this scale function is actually setting the current matrix to have a scale value associated with it. And then the next function is calling this GLUT wire cube, and this just renders a wireframe cube. And that was the cube we actually saw when I ran this example. And so that previous scale function kind of scales it out. So the scale is saying, pull it out, make it twice as tall as it is wide, effectively. And so it's like a tall cube that we see. And the flush is just saying, I'm done with OpenGL commands, render it, draw it on the screen here, effectively. So that's the display function, and let's real quick, the reshape function. So this gets called every time the screen size changes. So it'll get called once when you initialize and it creates the window. And this is just a good way to set up kind of information about the display that you're rendering against. So it goes in and it calls some functions, like there's a viewport function, and the viewport in OpenGL is kind of like a mapping between your computer screen and your 3D world. And so all of this function is really just defining that mapping. I won't get super into it, but it's basically you're setting a projection matrix, and in computer graphics you'll see a lot of a concept of like a projection matrix that defines how to map from the screen to your 3D world. Because your screen is 2D, your 3D world is 3D, and so there's actually a matrix transform that has to happen there to do that transformation. Like if you didn't do a transformation, you could just have a very simple, no perspective at all. Like you look at something and it's just flat, you don't see the sides around it. But there's actually equations that you can apply to say, make a perspective that looks like what you'd see in the real world. So like, a human, you have like, I don't know, 120 or so degrees of vision, something like that. And so you see, the perspective of the world around you, like something farther away is small, versus if it's really close to you, it's really tall. And that's the perspective as things change, and kind of as the further away they get, the smaller they get. And so that's what this does. It applies that perspective, and the perspective kind of changes based on the size of the screen. And this GL frustrum, this is kind of defining like what's the volume of 3D things we can see. If you look at like the Red Book and OpenGL kind of getting started stuff, it goes into a lot more detail of like what is a projection matrix. But basically this is just like the standard kind of boilerplate to say, create a 3D scene that's like the real world. Like, it's got a similar kind of perspective as a person might see. And then the keyboard function, this just gets called when the keyboard key is pressed. And it looks like it's just hard coded. I think the escape key is what it's looking for. Character 27, I guess that happens to be the escape key. So okay, I'm going to save this, and I'm just going to run it again because I changed the background to red. So in theory, we should see a red background when I run this. It's going to run the cube.py, and oh, that's interesting. It didn't do a red background, so not sure why that clear color didn't work in that case. But oh no, duh, because I'm not running cake.py. I'm modifying cake.py, but I didn't run it. So I'm going to do python cake.py. Now we should see, there we go, there's the red background. So again, looking at this, now that I kind of walk through the code, you can see how it's a tall cube, and it's it's been stretched out vertically, and that's because of this little scale function here. So it's scaling it out vertically twice as large as it is horizontally. So okay, so now what I want to do is, wireframe is cool, but 3D is cooler. So let's make this into an actual 3D shaded object. So there are a few things I need to change here. One thing is I need to change this from a GLUT wire cube to a GLUT solid cube. So I'm going to do that. And then the shade model, I'm going to change this to, I think it's GL smooth, but let's look it up just to be sure. So let's look up GL shade model. So yeah, I can select flat or smooth. So yeah, GL smooth is what I want. And so now let's just run this and see what it does. And I should get just basically a white cube. And so that's because the cube is right in front of the camera. It's not offset to the side in any way. So I can't really see any dimension to this cube. So let's move the camera over a little bit and have it look at the cube from an angle. So I should be able to see like the corners and the edges of the cube in here. So to change the camera, I need to change this GL look at function. So I'm going to change the position. Let's slide over and up 5. So it's going to go 5 to the right, and then 5 up, and then it's still going to look at 0, 0, 0, the origin again. So let's save this, and then let's go back and run that one, and we should see something different. So it's different. You can see it looks like a cube that I'm looking at from an angle, but I can't actually see any definition, of the sides. Like all of the sides are the same color. There's no shading at all. And the reason for that is that the fixed pipeline needs to have a light in order to see, if I want to see like one side of this cube brighter than the other, then that means that there's probably a light that's closer to that side of the cube. And right here we don't actually see, I'm not defining any lights. And so that's why it's just getting kind of this default everything is full brightness kind of look. And before it looks like my cat's a little bit excited. She might join us here in a second. So I know OpenGL, it's very exciting for the cat. So, okay, so let's add a light. And to do that in the old OpenGL fixed pipeline, it's a little complex, but it's not too crazy. So what I'm going to do is I'm going to steal a little bit of code from another example. So let's go to this move lights example. And I'm going to pull out a few things. So like this enables lighting, and maybe this actually isn't the example I wanted. There's a better example in here somewhere. Maybe it's the scene example. Yeah, this is the example that I wanted. So, okay, so let's pull out a few things that I need to start doing here. So let's pull out these functions that enable the light. So let's put this in my init function. So I'm enabling lighting. So this is a function you have to call. Now there we go, the tabs are a little bit messed up. So enable lighting, enable light 0. So in the fixed pipeline, there's a fixed number of lights that you define. I'm enabling the depth test, and so that's enabling the depth buffer, which is that optimization I was talking about, so that it doesn't draw things on top of other things. So let's see, so enable those. Oops, there's a little bit more I need to do to enable this. So I need to create a light, and the way this code works is it just creates some different options for the light and then sets it. So let's put the light up here. So do this, and then we'll fix the tabs. So what this is doing, actually here I'll kind of space this out a little bit. So it's calling this GL light function. It's changing properties on light 0. So each light in the fixed pipeline has ambient, diffuse, specular, and a position. So these are just parameters that define the light. You know, when you get into computer graphics, you learn about different types of light, and like ambient is just the light applied to every point. It's kind of like, you know, just the level of light in a room. Diffuse light is like the natural light from all the reflections in the room. So, you know, like the color reflecting off of me is diffuse light. Specular lights are lights from highlights. So like, you know, there's like some shininess on me. And so that's like there's a light that's shining on me, or I guess it's coming from this way, and then it shines into the camera. And so that's like a little specular highlight that you kind of see there. So you can change all of that property, so like your specular light component could be a different color from your diffuse light. We're not going to get that fancy. And in fact, this code, so it's just setting all of these light colors to 1, 1, 1, 1. So it's basically white light, like it's full. All the colors are set to 1. And I'm actually, they set it in an array here. I'm just going to set it in the actual function call. So we'll set the color of all the lights. The ambient light, they actually set to 0. And so that just means that there's no ambient light applied to this. And so we'll maybe play with this once we get the shading going and kind of look at how this changes things. Now the position, this is pretty important. So this is where the light's going to be in the world. So let's just delete this code that I'm not going to use. And so this is putting the light at 1, 1, 1. So it's, you know, positive X, Y, and Z axis. I'm going to move it out further, and let's just put it at like 10, 10, 10. So I'll put it kind of behind the camera, because remember the camera's out at 5, 5. So I want to put this thing even further back out behind the camera. Okay, so we define that light. Now let's see, what else do I need to do for this? There's a little bit of extra stuff. So when I clear the buffers, I need to clear the depth buffer in addition to the color buffer. So I'm going to copy out that bit of code here, and we'll put that in here. And then there's a little bit more of setup I wanted to do. Yeah, so you have to tell it to use the depth buffer here. So I need to go in and set the depth buffer in here. So this is just telling it when it initializes, use the depth buffer. And so, you know, that's effectively what it's doing. Now I think this is all that I need to actually start seeing some shading on this. And let's actually go back, let's change that clear color back to 0 to black, just so that it's not creating any weird, confusing things. So okay, let's run our cake.py and let's see what this looks like now. So okay, we're getting somewhere. So you can kind of see now, there are a couple different faces to this cube. So, you know, we're basically seeing the light reflecting off of a couple of different faces of this cube. And because the surfaces of this cube are perfectly flat, and I don't have any fancy shading applied to it, like this isn't, a rounded object, you're getting that kind of old blocky computer graphics look where, you just have flat shading effectively. But let's make things more exciting. So let's go beyond just a cube. Now the cat's going to pay a quick little visit. There we go. So let's change this into like a cylinder. So I was kind of thinking a cake. If I take a cylinder, think of like cylinder, that could just be like a round cake body. Then I'll put some candles on top. They're just other cylinders. So it's not fancy, but hey, it'll be at least a cake, computer cake for this. So, okay, so to change what I'm rendering, I want to change from GLUT solid cube to GLUT solid cylinder. And so GLUT has a bunch of different rendering functions that are super handy. Again, they use that older style of OpenGL, so like you can't really use this kind of function in modern OpenGL, which I think is kind of sad because it's harder to do stuff like this when you're starting out. Like it's much easier to call these functions. So okay, so the solid cylinder. Now, unfortunately, the documentation for PyOpenGL doesn't have this function documented, but it's in there. So it's GLUT solid. You can actually see all the ones that they document in here. So the cone, cube. But if you look this up, let's see, we'll just search for GLUT solid cylinder, and I think, yeah, this man page tells us. So it takes in the radius of the cylinder, the height, and then the slices and stacks parameter, which I'll talk about those in a second. So first let's kind of set this up. So let's create a cylinder, and so the radius, let's make it two units. Now these units don't have any meaning in OpenGL, so it's just 2 camera units effectively. It's not 2 miles. I mean, you could scale everything down in your world. It's just however you want to define it. But anyway, so this is a 2 unit radius. Let's do 1 unit high. Now the slices and stacks, because when you render things with the hardware, really the graphics card is like a triangle renderer. It doesn't know how to render a smooth surface. You have to break that surface down into triangles, and then you can render those. And so when I'm rendering a cylinder, it has to be broken into triangles, and the slices tells you how often to break the circle up into points. So if you use a small value, like let's just say like 5 here, or how about 6, we'll make it even, then it's only going to slice this up 6 times, and so you'll get like a blocky cylinder. Versus if you use like 32 or 100, you're going to get a lot more slices, and you'll see things are smoother. Let's just do 6 and see what happens. The stacks, this is how many vertical slices to take, which I don't think we really care about in this case. Like it's, we're not changing our height, the model in its height, so let's just do 1. So okay, so let's save this, and now let's run this example and see kind of what happens here from here. So okay, so now we're seeing something. It's a little hard to tell. Let's add another light so that I can start to see more of this thing illuminated. So let's see. We'll just copy our code. So to add another light, I basically just need to set up light 1 just like light 0, but I'm going to put it at a different position. So we'll do light 1. It's going to be the exact same color, but instead of going 10 to the right and 10 up, let's go 10 to the left and then 10 up again and 10 out. So let's do -10 on the x-axis. So basically I should have like 2-point lighting where like, there's 1 point up above, another point over here, and they're both kind of shining down on this object. So let's save that. And then I also need to enable this light. So we need to call GL enable. Do this. So okay, now let's go back, and let's run this example, and hopefully it should be lit a little more. So okay, now we can kind of see. So now I have a light on both sides, and remember my camera is off to the side and up a little bit, so it's kind of looking at the profile of this cylinder. But we can see now, let's change this 6 to like 32, so this is that number of slices, and see what this does to the model. So if I run this, so okay, now this is starting to look like a cylinder. Like you can see it's smooth looking, the light kind of evenly changes as it goes around. And that's because I've subdivided it at a much smaller level. And because I've set things to use smooth shading, so like in my initialization function, I'm using the smooth shading, you actually can't tell. So even though this thing is only divided 32 times, it looks like it's perfectly shaded. And that's because smooth shading actually can look at a polygon and say, okay, like a triangle, you're a part of a larger curve. And the normal, which is another very important computer graphics term, the normal is a vector that kind of points opposite to where an object is. Like you kind of use the normal to figure out how light reflects off of things. And so the normal can change over the surface of a triangle. And if that changes, then it changes how it's shaded like this. And so I think a good way to visualize this is let's put it on flat shading instead of smooth shading and see what changes for this. So I'll change my shade model to flat, and then let's rerun this and see what it looks like now. So, okay, now you can actually see like each of those 32 different divisions around this circle is like you can see each triangle or each face is like a flat square on the surface of this cylinder. And that's because it's not doing smooth shading. So it's not looking at the normals. It's not interpolating the lighting across this cylinder. And so, you get this kind of old style computer graphics effect, which I actually think is cool. Like I'm nostalgic for flat shaded stuff. Way back, in the early 90s when people were making 3D engines, like this was the best you could do. And I think it's kind of cool. I think it needs to make a comeback for that kind of style. But let's put it back on smooth just so we can kind of see, shading of things. So, okay, so we've got a couple lights. We've got smooth shading. The cake's not rotated the right way, though. You can see it's kind of, like let's make it longer. Let's make it, maybe 5 units long and see what this does. So, I want the cake to be, so you can see it's like, okay, it's this weird kind of rotated thing. I want it to be facing, up and down like a birthday cake should look. So let's put this back to 1. So what I need to do is I need to rotate the model. And the way you do that, like I was saying, there are different matrices that are applied at different levels. And actually, maybe before I do that too, so there's this scale that we're applying to this, and maybe we can kind of tweak this, but let's turn this scale off, the scale function here, and let's just look at the cylinder as is, like without any scale applied to it. So let me just escape out of that. And so now you can see this, okay, this looks a little more circular. The cylinder we were looking at before is kind of stretched out because of this scale. But basically this scale is just changing a matrix, which changes how this object is rendered. So if I want to rotate this thing, I actually can just call the GLRotate function. And let's see, if I remember correctly, it's GLRotate F. And let's go back and look at the documentation for that. Yeah, so GLRotate. Now you don't see F at the end of this, or I guess you see F at the end of this. That's just an OpenGL convention. Functions that take floating point values end in F. So if you see that in OpenGL code, that's kind of what it means. And so you can see there's like a D version, that takes a double. And then there's nothing, that takes an integer. And integer you probably don't want to use for rotating. You probably want to rotate like some floating point value, like a real fine, precise value. But okay, so rotate takes an angle and a vector to rotate around. So what I want to do here, so I want to rotate F. I want to rotate 90 degrees around. I want to take this cube and I want to flip it on its side effectively. So just rotate it 90 degrees. And the axis I want to rotate it around is actually the x-axis itself, so the left to right axis. And so, I mean, it's a little hard to kind of describe it. Let's just try it. So to define a vector on the x-axis, I just need to say 1, 0, 0, because this is basically saying go 1 unit out along the x-axis and then no other units out along other axes. And let's see what this does. So if I change that, and then go back and run my example again. So okay, now we flipped it over, and let's not do 90 degrees. Let's do like 45 degrees just to kind of see how things change as you rotate it. So I'm rotating around the x-axis, and now you can see, so it's rotated 45 degrees around the x-axis. And so we're getting closer to kind of flipping it on its side. Now I've done this before, and I know I want to rotate it negative 90 degrees, because the way I'm rotating it right now, when I increase the y-axis, when I move up, it's actually going to move down because I flipped the whole model upside down. So I want to rotate it 90 degrees the other direction to make sure that it's facing up. So I'll do that, and then let's just save. Oops, let's run this again. And we should see. So, okay, cool. That's cake-ish. It's at least the general shape of a cake. Now let's add some candles to this thing. So I want to add some extra cylinders to this. And let's see. Let's get rid of this scale function. I'm not going to use this thing anymore. So now to do this, I need to create some more cylinder objects, but I want to move them a little bit. So I want to, right now this cylinder is being rendered from 0, 0, 0, like the origin, because I haven't told it to move anywhere. Now there's a function called GL translate, which will move your current position, or it'll change the position of things that you're going to render after this. So I can say, okay, so let's translate this, and let's move it 0.5, 0.5, oh no, 0 and 0.5. So this is going to move a little bit along the x-axis, like the left to right axis, and then a little bit along the z-axis, which is kind of the in-out axis. It's not going to move it up and down, it's just going to move it, forward, backward, and then left, right a little bit. And so we'll kind of offset it a little bit that way. And then let's render a cube or cylinder again. So let's just copy this. And let's make this one a lot smaller. So the diameter, let's do like 0.25, because candle is real thin diameter. But let's make it taller. So let's make this 2 units tall. I'll keep the same 32 subdivisions. That's fine. So let's save that, and let's run this now and see what we get. So okay, so there's basically a pole sticking out of our cake here, effectively. And let's play around with moving this thing a little more. So let's move it. Instead of just 0.5 along the x, let's move it 1.0. So this should kind of move it more to the right. And actually what we could do, let's move this, and then we'll move the camera back to looking head on, because right now the camera's kind of offset a little ways. So we'll move the camera back so we can see this kind of, and the movements make a little more sense. But yeah, let's just move this and see how it renders now. So it should be, so yeah, it's moved a little bit further along. But let's reset our camera so that it's back at 0, 0, 5, 0, 5. Yeah, okay. So now the camera, it's moved up a little bit and back a little bit, and then it's going to look down at this object. So let's re-render this and see how this looks. It should just be a slightly different view, but it should be easier to see. Okay, now it's a little more apparent kind of what's happening here. So you can kind of see I've got the candle sticking out, and let's move this thing. So if I go even further, let's say like 1.5. So this is the x-axis. This should move it over to the right a little bit, because I've just increased where I'm going to translate this thing to. So yep, looks like it moved over to the right. So let's keep it at 1.0. Now let's move it back further. So the z-axis, this controls the kind of forward backwards. And let's actually move it like -1 and see where that places it. So we'll render this again, and oh wow, I put it somewhere. I think I just moved it behind the camera. So this is the other fun thing when you do graphics program. It's like things disappear. Where did I put it? Oh crap, I put it somewhere I can't see. So let's try this again and see what happens. So okay, that makes a little more sense. That's a little weird. It looks like I'm moving it along the wrong. Oh right. So here's the thing. I've rotated my cake, and so this rotation here is actually changing how this translate behaves, because basically this rotation says, okay, flip yourself 90 degrees over, and or I guess 90 degrees, so it's it was on its side, now it's down. And so now the z-axis is in a different position. So my z-axis is actually effectively my y-axis, my up-down axis, because I've rotated these axes. You can fix this though. There are ways you can change this to say, I want to build this birthday cake model relative to the cylinder that defines it. I'm not going to do that, so I'm just going to mess around with this, and let's just put this at 1.1. I think now the y-axis is my z-axis, so let's go back and re-render this thing, and we should see. So okay, so yeah, so now my y-axis is basically my back-forward axis for this object. So now I've put a little candle in the back, and let's put another candle somewhere. But the problem is, so now if I want to translate again, so every time I call like translate or rotate, it's going to apply this translation relative to the previous one. And so that makes it a little hard in that, like, if I want to put 4 candles on this thing, I can move to the position of one candle, and then I need to figure out like how to move to the position of the next candle. Whereas maybe I want to make these positions of candles relative to like a fixed starting point, like the center of this cake. So the way to do that, you can actually save the matrix state in OpenGL. So you can take the current translation and rotation matrices and save them. You can make some changes and render an object, and then you can restore those back. So it's like a queue effectively, like you can, or a stack rather, where you can push the current state onto the stack, render stuff, pop it off, and then go back. So let's do that. So let's do, it's a GL push matrix command we call. And then we're going to translate, so we'll move over, render our candle, and then when we're done doing that, let's call GL pop matrix. And so that will, so push matrix kind of says, okay, save the current matrix state. Now I'm going to do some changes to the matrix state, and then pop matrix says, go back to the previously saved matrix state. So this should put us back to where we started before we move that candle around. So I'm going to save this, and we'll just run it, and we shouldn't see any change. Like nothing functionally just changed. So yeah, candles in the same spot. But now I can go in and say, okay, now I want to render some other candles. So let's move these guys out to a different spot. So we'll put in another one, and messes up the formatting a little bit. So okay, now this candle, let's move it over in the x-axis. Let's go -1 and see how this works. And we're going to render the exact same type of cylinder, so same diameter, same size, that type of stuff. And let's see what happens here. So now I've got 2 candles. Cool. So you can see how basically I rotated this cylinder, created my cake, and then I said, okay, save the current state, move your position, render a candle, go back to your starting state, move to a new position, render a candle. So like, let's see what happens if I pull these pop and push matrices out, and just if I was just calling translate, and like wild things are probably going to happen, and we might not even see the second candle. But basically the second candle, so yeah, you can see it's totally different here. This second candle now is relative to the position of the first candle, and I don't really want that. I mean, I could do that, but it's going to get really confusing, because now, next year when it's the 5th birthday, I need to add a 5th candle. I need to figure out like what was the order I created all these, and what's the translation I need to do. So forget trying to do that. It's much easier to just save the state and recreate the state. So that's why it's useful to do this push and pop. Now let's create the other candles that we need. So I need 2 more candles on this cake. So we'll create these, and let's see, these now I want to move forward and backward a little bit. So I'm just going to invert this and say, the other candles were pushed back, so this one will be pulled forward a little more. And then I also want to make one on the left side and one on the right side here effectively. So let's save that. Let's run this. And okay, cool. So it's cake-ish. Let's move our camera down so maybe we get a little shallower angle on this thing. So it's OpenGL cake. This is what you get for that. Okay, so this is the z-axis. This is the height of the camera. So let's cut it by half. Let's like 2.5. So we should see like more shallow angle on this, and see. Oh, no, that was not right. So basically, it's like I moved it up more. What did I do to this thing? Well, let's see. So I'm looking at it at a higher angle than when I was. Oh no, I know. Sorry, I did the wrong thing. So I just moved the in out the z-axis. I just moved closer to it basically. I don't want to do that. I want to move the y-axis, the up-down axis. So let's make this 2.5. So we'll save this. Now let's try. Now we should see a little more shallow angle. So okay, there we go. So that's cake-ish. You know, there's maybe if we make the candles a little smaller diameter, let's do like 0.1 diameter for the candles. All right, so we'll do this. Save that. All right, now let's render this and see what happens. Okay, that's starting to look like a cake. That's not too bad. Now let's change the colors of this thing. So in the OpenGL fixed pipeline, there's a whole set of materials and things you can do. I'm just going to go and let's copy a few things out. I did this in another example, and I can't remember if these other examples use it or not, but there's basically a material that we need to enable for this cube object. So let's see, let's go back, and I want to say it's GL enable, and it's like a GL material something or other. Let's look up in the reference here. So GL enable, oops, I need to go back, and let's see, does this tell me what I need to enable? No, it does not, unfortunately. So okay, let's go back to the examples. One of these has to have an example in here of materials. Let's see if like moving the light might have this. Nope, that's not it. I have an example here that I'll open up that I was playing with earlier, so we'll use this. Yeah, so it's right, GL color material is what I need to enable for this. So if I call GL color material, so this is basically telling it that materials can have color assigned to them. And right now my display function is just setting the color to white. And that's okay for my cake. You know, maybe we'll say this is like white frosting on the cake. So, you know, when I render the cylinder, I'll just move that color to be closer to that. But now let's change the color of my candles. So let's, maybe before I render all the candles, we'll change the color. So let's make it like red. So we'll set red to full value here. And maybe I'll put in some comments here. So let's delete these comments. So we'll say clear the screen and depth buffer. We'll say set up the camera, viewing the origin. Now we'll say position, rotate, and render the cake. So that's what these functions are doing. And now change color and render the candles. So that's what these functions are doing. And let's run this and see what it does. So okay, cool. Now we've got red candles and the cake. So that's kind of cool. Now let's actually rotate it. Like, let's make this thing spin around a little bit. You know, because right now we're just fixed rendering. It's maybe not the most interesting thing in the world. So I'll show you how we can do that. So this will be kind of cool. What we want to do, so ultimately I want to rotate everything. So I want to apply another rotation. And the way I do that is I say, I can basically call the GL rotate function again. And this time, let's see, let's just rotate like 45 degrees. And I'm going to say now the axis I want to rotate around is the y-axis, the up and down axis, because this is before I flipped everything on the side. So the y-axis really is the up and down axis. And so if I rotate around that, then it should spin the cake around effectively. So I want to say my vector to rotate around is the y-axis. So if I do this, this should rotate the cake a little bit when we render it. So okay, so now we can see the candles are in a different spot. And now the cool thing is, I can just change this over time. So let's make a couple global variables. I'm going to need to keep track of the time, basically, like how long it's been since I rendered the last frame. So to do that, I'm going to import the time library. In Python, you can call time.time. That'll give you a floating point value that I think, from what I understand, is supposed to be the highest precision clock available. And so you get not necessarily nanosecond, but at least millisecond accuracy with time.time on the Raspberry Pi. And so that's probably good enough to be able to render things. Usually when you're doing a game, you want a really high precision timer so that you know each frame took precisely this many, like even nanoseconds if you can, to render, so that when you're doing like physics calculations and things, you know exactly how long the previous frame took, and how long you should simulate your world for the next frame. But anyways, okay, so I'm going to need to keep track of my last frame time. So I'll say last frame. I'm just going to say, how about time.time? We'll initialize it to the start. And I'm also going to need to say, have a cake angle. And we'll just start it out at 0. And we'll increase this over time, basically. So now at the start of my display function, I need to do a little housekeeping to update these variables. So one thing, because these are global variables, Python doesn't, if you want to change a global, you have to explicitly tell Python this function is going to change this global variable. If you don't do this, then it's going to assume that anytime I deal with last frame, it's a local variable to this function, which you don't really want. And you'll see global, it's kind of ugly. I don't like to use global. And generally the way that you get around this is if you create a class, you can have a bunch of class variables that are members, and that's where your global state lives. And so then you create an instance of that class, but we'll just keep this simple. We'll make global variables. So we'll say that both these are globals. So now I need to say my current time is time.time. And then I want to figure out the delta. So what's the difference between my previous frame time and my current frame time? So how long it took to render this frame, or the last frame rather. So I want to say delta equals current time minus last frame. And then I want to be sure that I update last frame to be my current time. So now delta tells me, it's like a floating point value of how many seconds it took to render the last frame. And so now I can change my rotation. So let's say cake angle plus equals some speed. So let's just say like 10. So this will go 10 degrees per second times my delta in seconds. So now my cake angle should change over time. And if I just change this 45 to cake angle, we should see this thing spin around. So let's do this. And nothing's happening. So let's see. I probably got something wrong in here. So I'm rotating the cake angle. Let's see. Plus equals 10 times the delta. That's kind of weird. Let's see. Okay, I did something wrong. So let's print out what I've done wrong here. So let's see. So at the start of my function, taking the current time, and then I want to figure out the delta. Let's just print this out. Oh, I know what the problem is. This is another dumb little GLUT thing. Basically, by default, it's not going to render unless something changes. So like if this window gets resized, I actually need to tell it to re-render the next frame. And it's this weird little function that you have to call. It's, this post redisplay at the end here. So I just need to go in here and say, okay, so this is basically going to say when I'm done with this rendering of this function, re-render it again, even if nothing has changed, like even if the window hasn't changed, just keep re-rendering it. And so that's going to make sure that my function gets called again. So let's rerun this, and now we should see spinning cake, hopefully. Yay, look at that. We've got a spinning cake here. So I think that's all I wanted to do. Just some super basic OpenGL with Python. If you want to go further with this, definitely check out the Red Book, OpenGL kind of programming guide. And in particular, check out, I'll put a link in again to this modern OpenGL with Python guide. This is what you want to look for if you're really learning OpenGL. What I just did is using the old fixed functionality pipeline. I think immediate mode is sometimes what it's called. And in modern OpenGL, you can't do what I just did. Things like saying, hey, create a light at this position. You actually have to code the equation for that light in modern OpenGL into a shader. You actually are effectively implementing this rendering equation. But that's a lot more code. It's a lot more overhead. It's not complex. Like, it's just a lot of boilerplate. And unfortunately, OpenGL moved to this programmable pipeline, which is awesome. Like, I'm not faulting them for that. It is the right thing to do. It's the performance that you need. But they kind of lost the simplicity of that immediate mode rendering or the fixed functionality pipeline, and nothing has really stepped in. It would be great if somebody created a library that used the programmable pipeline but let you do things like the old style OpenGL. And unfortunately, I don't know of any library yet that does that. And so, it's fine to go back and use that old OpenGL style, but just realize, if you go to a game programmer and you show them your cool little OpenGL script, they're going to laugh at you and be like, where are the vertex buffer objects? And you're calling GL vertex? This is insane. So, this is maybe not the right way to do it these days, but it still works and it gets good examples. And it's kind of cool that you can see, you can play with the Raspberry Pi. Now, when you flip on this OpenGL mode, you've got a real version of OpenGL. It's not the OpenGL ES mobile version. Much faster performance, like we saw when I ran the GLX Gears demo. We could barely get 6 frames per second, and it was a flickering mess. Versus with hardware enabled, it's beautiful, 60 frames per second, and perfectly smooth. So, I think that's all I wanted to do. I don't see any, or I guess if people have comments or questions, maybe ask them in the chat right now. And then, otherwise, check out Adafruit's YouTube channel, youtube.com/Adafruit. You can see videos. I'll post this video up and put some links into it. Check out the Twitch, twitch.tv/Adafruit. That's where I stream these things live to. Usually I stream on Fridays, but special day for the Raspberry Pi's anniversary, so I figured I'd flip on the camera and just have some fun with OpenGL here. So I think that's it. I think I'll end the stream. So thanks a lot for watching, everybody, and tune in. Oh, and also I guess, so Wednesday will be Show and Tell and Ask an Engineer. So definitely tune in and watch those. And then Thursday is 3D Hangouts with Noah and Pedro. So thanks a lot, everybody, and I'll see you guys Friday.